Let's move on to our next speaker, who is Jamie Lin from Qualcomm Research. He's a principal engineer at Qualcomm AI Research, where he works on neural network architecture and acceleration design. And Jamie, I'll hand it over to you.
In this session, we are going to talk about the I call it tiny orchestra. So it's basically some of the challenges the designer for the tiny neural network would face, and some techniques that we could overcome those challenges. Okay. So we know that the deep learning is going to be more and more pervasive going forward, and a bunch of use cases and services for business, for commercial, and for entertainment and so on are happening all over the place. So we see that, so there are a bunch of use cases, right? For smartphone, wearables, for automotive, for AR, VR, speech, audio, and sensors, and so on, just to name a few. So some of the use cases are shifting actually from the cloud to the edge devices. And some of the reasons could be, you argue that the data locality, so the latency would be better if deep learning inference is done on the edge. And also some reasons could be like personalization, because if the services are customized or personalized for the users, it could perform better. And also the concerns of user privacy and so on. So for some of those reasons, the deep learning places are on the edge side. But inevitably, there are challenges facing us, right? When we try to perform those services on the edge devices, depending on the resources of the edge device, it could be very, very limited in the compute resource. For example, the computation capacity, capability, and the memory size versus the cloud, and also the latency response that we are facing when we shift the design and the inference targets from the cloud to the edge. So we would need quite a great deal of optimization to really perform the full efficiency, given such new design paradigm. So I believe many of you have been seeing many different types of neural network architectures, right? And for example, we are all familiar with some popular types of neural network architectures like ResNet, MobileNet, which are more conventional with the popular and regular building blocks like the residual blocks or bottleneck blocks, where we try to repeat the same block of design several times, and then we don't really need to go with like different complicated design for the model. Yet we're able to achieve quite complicated tasks already. But in recent years, new types of neural networks has emerged. So those are more the specifically optimized based on the given constraints, or even for different target platforms. So for example, if you really want to achieve best performance on a particular platform, let's say a RISC processor or a CPU, then instead of using the general popular conventional neural network architecture, we might be able to put some hardware design constraints into the design, such that we may be able to use the neural architecture search to, given those constraints, to search for the optimal performance targets. So for example, if you want to minimize your latency, or if you want to minimize your power consumption on a particular target, then you may be able to use this type of NAS or neural architecture search derived networks. And this is good, but on the other hand, depending on the constraints you place in your architecture search, you may come up with a very exotic design of the building blocks, or not even building blocks. It could be quite irregular in the network architecture. So for example, here on the left-hand side, you see the RAN wire, which is a special type of network. And it could be an extreme example, but this is just to give you a flavor that a neural architecture search network could have very irregular connectivities in the network graphs. And another example is the SwiftNet at the middle. So if you kind of compare the two types of neural networks, you can see that on the right-hand side, you see the plot which shows the top one ImageNet accuracy for classification over the computation complexity. So you see that here, it seems to be two classes of the network architectures in this figure. So the bottom figure is in the red are the more regular or conventional types of architectures, like ResNet, MobileNet, and so on, as opposed to the top cluster in green for the neural architecture search-based networks. So you see that like RANwire, MNASnet, and a bunch of different NAS-derived networks. So apparently, the NAS-based architecture could perform better given the constraints that we intend for those type of networks. But on the other hand, you can see.
Jamie, your slides seem to have frozen. Can you do a refresh and let us know which slide you're on?
Oh, okay. Okay.
They've not been advancing, so.
Okay, let me try to. Maybe let me try to share the desktop again. I think. Okay. So can you see the slide now?
Yes, yeah.
Okay. Okay, so let me share that. Yeah, it's strange that when I put on the presentation mode, it switched to other terminals. So maybe I'll keep in this mode. Would that be okay?
Yeah, that's fine.
Not the presentation.
You can say
okay. Okay, great. Yeah, so let's continue. So yeah, so as we see, let's go back to slide 3. So yeah, so you see that there are two types of networks, and it seems that the NAS type will perform significantly better given the intended constraints, like target constraints or other design constraints. So now the challenge is, given this type of network, how will we be able to schedule for execution? So if we go back to the next, okay. So in slide 4, so I believe you can see slide 4, right? Okay. So on slide 4, so we typically can model the neural network in a graph and try to perform optimization on the graph for the model. So on the bottom left figure, you see that this is a typical type of the, this is a typical type of the convention model, which is quite linear. So this is like for the like ResNet or MobileNet type of models, where you see one convolution layer followed by another. So in this type of networks, the scheduling is pretty trivial because all you did is pretty much you execute one convolution layer, and then after it, you execute another layer sequentially. However, in the NAS-derived networks, the connectivity may not be linear anymore. So in that case, you can see quite irregular or random. I wouldn't really say random, but it's irregular connectivity from multiple nodes of convolution to other set of convolution nodes. So you may wonder, how would we be able to schedule this type of network? And how can we say that this scheduling is optimal? given this network design. So in the next, we will talk about an interesting experience that our team had back in 2019. It was in the Visual Wake Word Challenge in CVPR 2019. And this challenge was organized by Google AI. So in this challenge, so the challenge use case is for person detection to detect from between a person is present versus person is not present given a picture of test sample. So our goal is to lower the compute resources while maximizing the accuracy performance. So the competition is to compete on the accuracy given the resource constraints where the model size has to be smaller than 250 kilobytes. And as a comparison, the MobileNet V2 is easily having like more than 3 megabytes. And then all the weights are stored in the flash. And the second constraint is the peak activation memory usage should be lower than 250 kilobytes because the activation memory needs to be stored in the SRAM on chip, and that memory size is quite limited. So you can see that the memory requirement is very, very stringent because both weight memory and activation memories are under 250 KB. And the total MAC complexity per inference needs to be smaller than 60 million flops. So these are some of the competition participants. And in the result, there are two categories of this challenge. MIT won the first category, which is deployable in today's framework, the TensorFlow Lite framework. And the second category is deployable in the next generation framework, in which our company won this competition. So the reason why we mentioned about this experience is I want to showcase our design to give you a sense that how the efficient execution could be handled through the optimization in scheduling. So here, let's see the example. So this is the network that we used in our neural network architecture search-based method. So the NAS search generated such irregular, as you can see, irregular connectivity in the network. So you see that there are so many different nodes. And also the nodes are connected in quite irregular way. So you see that some nodes are having multiple input connections. So after the design, our model is yes within 250 KB, and the max is also within 60 million max, which are all satisfying the constraint. And our achieved accuracy is 95, more than 95% for the person, no person detection. But then the question is, what would be the peak memory consumption for this model? Because there exists multiple ways to schedule this type of network. So the computation result input and output are identical, but you could schedule in several different ways. In fact, not just several, a large number of different ways. So then we kind of come up with, so I would really like to show in the, okay. So this is the result we came up. So here we try to use a manual scheduling method to solve this problem because we have to come up with a scheduling plan that achieves smaller peak memory usage than 250 KB. So we try to use a dynamic programming method, but manually to kind of schedule this model. And if we look at the execution node by node, you can see that since I can not show animation right now, not in the presentation mode, but this is on the left figure, you see the red dots. There are the memory consumption for activation, starting from executing the first node and then followed by the second and so on. So you can see that the red dot shows the peak activation memory consumption at the snapshot of that execution of the node. So you see that the peak execution requires 200 KB in the total 250 KB activation memory. So this satisfies the design constraint. And if we don't do this dynamic programming based scheduling, our memory consumption is actually 3x larger using a regular TensorFlow-like framework. So the question is, how will we be able to automate all these, since this method may be used in many different architectures and so on. So, and then in this slide, you see this is a result of our computation. So on the left, you see the accuracy versus peak memory usage. So all the participant teams are under 250 KB. And then on the right side, you see the accuracy versus complexity. And then where all the teams are like here. So yeah, so the result is that we need to use some optimization techniques to ensure the global optimality given the constraints and the design. So here I cannot really show the animation, but just to give you a sense that given an example network, you are able to use the dynamic programming techniques, which we apply in also many other problems. And in this problem, it can help automate and find the global optimal solution given this scheduling problem. Okay, and then in the next slide, here we kind of talk about two additional techniques that we used to relax the design constraints. So feel free to check out the reference I put in the last slide in the deck. So these techniques could be like channel-wise partitioning and kernel-wise partitioning, which could enable relaxing the design constraints by enforcing partial sum computation, such that you don't really need to wait for the completion of all incoming connections before you can start executing convolution for the node. So you can simply wait for the arrival for the very first connection input, and then work on a partial sum for the convolution, and keep the results in the accumulator for that node. And then when the next connection comes, you keep doing the partial sum until you finish all the inputs. So then the scheduling can be relaxed, and you don't really need to be stuck with a particular node before you move on to the next node. Okay, and then in the next slide, we kind of show the result in our analysis, given several different types of NAS-based architectures, where the reduction in peak memory can be achieved by the dynamic programming method. So if we compare between the DP-based method and a regular, like TensorFlow-like method, which did not really enforce the optimization today, you see the reduction in peak memory can be up to 3.4x. And of course, this number depends on the particular network topology, as well as the complexity of the procession tasks. And all the scheduling cost is quite insignificant. It's like the compiler spending less than 1 minute to finish searching for like millions of possibilities, given the complexity of the network. So for those of you who are interested, please feel free to check out the paper.
Hey, Jimmy, so, we'll have to start wrapping things up.
Okay, sure. Okay, so so next topic is, I'll be quick. So this one is regarding the second type of the problem, where we try to optimize for the memory access reduction. So given a network, we typically have on-chip memory as well as off-chip memory, where we try to store weights and activations among them. So the problem is the memory access consumes power, and in order to keep the power consumption low, how will we be able to reduce or minimize the memory access such that the memory consumption, the power consumption can be small? So, so here, so we just provide some quick concepts. So the liberal scheduling is the typical way we did in today's linear model, where we don't really do optimization for the depth first scheduling at all. We only do layer by layer memory access. As opposed to the second type, which were enforced depth first scheduling for optimization. So we want to keep activations in local memory and then minimize the need to access the off-chip or non-local memory. So if you see the figures, you see in the typical liberal scheduling, you pretty much do the memory access once every convolution in the liberal approach, as opposed to the depth first scheduling, where we try to reduce the memory access. So my final slide. So there are basically three categories of the approaches. The first is layer by layer, which we pretty much did today for the simple linear model. Or the second type is non-global optimization algorithm, which is simple and it's typically the greedy algorithm. So we try to keep the memory full, but we don't really need to release a part of the memory until it's really full. As opposed to the final type is global optimization, we typically can use a dynamic programming to achieve it. So a summary. So scheduling problem is important in the performance of the neural network, especially for the constraint, high constraint, tiny neural network case. So the network graph scheduling against peak memory consumption can be quite useful. And the second technique is the depth first scheduling, and with the, for example, the optimization using dynamic programming against the amount of non-local memory access can be also quite useful. So that's the end of my presentation.